Hi. So we recently finished our discussion on the on policy Monte Carlo algorithms, and in this lecture we're going to be shifting our gears a little bit and start talking about the off policy prediction via importance sampling, or also for Monte Carlo algorithms. So one thing to note is that in the previous lectures we had made a certain distinction between on policy and off policy algorithms, where we said on policy algorithms, they try to improve the same policy that they use to generate behavior, where this is not the case in off policy algorithms. So this is a distinction that will become more clearer after this lecture, right? And before we actually get into the core material here, I'm just going to give a little bit of a high-level overview of what we actually went through in the previous lecture, as this will give us the motivation we need to start the content that we're going to be discussing in this particular video. So let's actually start. So in the context of on-policy algorithms, we say that we're given a pi, some arbitrary policy, and we would use this pi to generate episodes, right? So we would use this pi to generate some episodes, and then using these episodes that we generated, our goal was to estimate our Q values, right? So the Q values of some state action pair, right? And what would we do? We would take the argmax of those Q values, and this in turn would give us a new policy, pi prime, or whatever you want to call it, right? So this was the idea, but the problem is this: when we look at this sequence, we see that all the actions that we're evaluating and the argmax that we're taking here, it's all dependent on pi. It's all dependent on pi here. So if pi does not explore some state action pairs, that means that the state action pairs will not be present when we're actually making our decisions. So we end up acting suboptimally if we follow this sequence. This was one of the problems that we saw in the previous lectures. And so what we had said was, if we denote A star, right, to be the argmax over all actions of Q S, A, right? If we denote A star to be this, then we would update our policy as follows: the probability of taking an action in some given state, which is how we're updating our policy. I'm just giving a high level of what we already covered in the previous lecture, so in case this isn't all clear to you at all, just watch the previous lecture and it will be much more clear. So this was the idea, that how would we decide on what action we would take? So with a probability of 1 minus epsilon, where epsilon is just some small number, plus epsilon over the cardinality of our action space, right? With this probability, we would take the optimal action, and then with the remaining probability here, we would take any of the other suboptimal actions. So why were we doing this, right? We were doing this because, like we said, if we just follow the sequence, we're gonna miss some potential state action pairs that might actually end up being more optimal than the ones that we're currently exploring. So this allowed us to do a bit of exploration, right? So we were able to do a bit of exploration because of this factor, right? That's what this allowed us to do. So having said that, right, this is what we were doing in the context of on-policy methods. But that's the thing now. This is kind of a dilemma that's actually faced by all learning control methods, in the manner of speaking. Because what we're trying to do here is we are trying to find an optimal policy, right? But this is all based on suboptimal values of QSA or whatever. This is what we're doing in this sense. And that will become clearer in a second. But let's actually turn back to what we were talking about in the beginning of the video when we start talking about these on-policy methods. These are actually, when we're talking about on-policy, it's kind of a compromise if you think about it, because we learn action values not for the optimal policy, but for a near optimal policy, right? That still explores. This is the whole context behind this kind of policies. So what off-policy methods say is, why don't we actually use two policies? One that is learned about and becomes the optimal policy eventually, and one that is more exploratory and used to generate behavior, right? So we would have two policies, right? This is the one we learn about and eventually becomes the optimal policy, right? This is what pi is. And then another policy. So now we're talking about off-policy methods, just so that you're clear. And the other one is more exploratory and used to generate behavior. So that's the idea here behind this off-policy methods. So we call pi our target policy, and we call B our behavior policy. Right? This is just notation, more or less. So pi becomes our target policy, B is our behavior policy. Pi is what we want to learn about and eventually end up becoming an optimal policy, and B is just more of an exploratory policy that we use to generate behavior. And this is known as off-policy learning. That's the idea here, right? So the problem now, maybe we might explore this in the next lecture or so, is that off-policy methods are often of greater variance and they are slower to converge, but they are more powerful and general. And if we actually look at on-policy methods, they're actually a special case of off-policy methods where the target policy and the behavior policy are just the same, right? This is the case that we have. So in this lecture, right, we're doing off-policy prediction. So as usual, when we start in a new topic, when we start in a new algorithm, as of yet, we first try to solve it for the prediction problem, and then we solve it for the control problem. So in this video, we're just going to be talking about the prediction problem. So we're talking about the prediction problem. That means both the target policy and the behavior policy are fixed, right? So what are we trying to do here? Well, as usual, we want to estimate V pi, this is what we want to estimate, right? V pi or Q pi as well, but I'm just going to use V pi here, right? But what do we have? Right, this is what we want. This is, in a matter of speaking, our goal. This is our goal. We want to estimate V pi, but let me use a different color for this. We have episodes following. So we have episodes following another policy, which we denote by B, right? And the idea here is that B is not equal to pi, so there's a different policies, right? Where we say B is the target policy. Pi is the target policy, and B is the behavior policy, right? This is essentially where we are right now. So this is what we have, right? So we want to use episodes from B in order to estimate the values for pi, right? But in order to be able to do that, we need to make sure that every action under pi is also taken under B, right? So what that means in mathematical terms is just the probability, if the probability of an action given some particular state is greater than 0, then it must follow that the probability of B of A given S should be greater than 0. So why are we doing this? This actually has a special term. This is called the assumption of coverage. Why? Because we are trying to use episodes that are generated by B to estimate values for policy pi. And of course, to be able to do that, we need to make sure that all trajectories that are taken under B, all trajectories under pi, we should be able to generate them as well under B, right? This is essentially what it means. So this is the assumption of coverage, because once we have some action that's taken under pi, but not taken under B, then it becomes a bit of a problem to kind of estimate. How do we actually start estimating? So we need to make this assumption of coverage in order to be able to proceed with this, right? So that's how this works. So now that we actually reached this point, one thing we need to know is that we can utilize a specific technique in statistics that is known as importance sampling. So of course this is something that we already mentioned in the topic here and in the title of the video, so shouldn't be that much of a surprise. So we are using a technique called importance sampling. Right? So what is importance sampling? This is just a technique for estimating expected values under one distribution. Let me try to write faster. Given samples from another. Well, this should be clear, because when we're trying to estimate the V pi, which is our goal, if we remember from previous lecture, we would do that by actually taking the expected value of the return, right, for various states. This is how we would estimate what V pi is. But since we have episodes that are following a different policy than pi, which is b, we utilize this technique called importance sampling, which allows us to estimate expected values under one distribution given samples from a different distribution, right? So that's the idea here. So we apply this importance sampling to off-policy learning by weighing the returns that we get from our target policy, from the trajectories that we have under the target policy and the behavior policy. So let me actually make that clearer in the next page. So if we remember from before, like when we were talking about the backup diagrams, so I think the backup diagrams here should help us visualize what we're trying to do. So if you remember, we are given a state S, right? And from this state, we try to take action, either A1 or we take action A2 or we take action A3. So we were representing this as, let me use different key. So let's say the probability of taking an action given I'm in this state. This is what this term was representing, right? There's a probability I might take A1, A2, or A3. So this is from one of the earlier lectures when we're talking about backup diagrams. Okay, so we've reached this point. We can take action 1, action 2, or action 3. And then after taking any one of those actions, we might end up in some state S prime. So this is kind of like, if this is a time step t, this is a time step t plus 1, right? Or we might end up in some state S double prime at time step t plus 1. Or let me use this since this is actually representing state, or some other state time step t plus 1. And then what's the probability of ending up in each of these states? We had said that this probability is represented by the probability of, so let's just say a given st here, and then this is st given, right? This is st plus 1, sorry. St plus 1 given st, comma, whatever the action is. So this is what this probability was representing. What's the probability I might end up in this state, st plus 1 or whatever, given that I'm in state st and I take action A. So this is essentially a trajectory we might follow, and of course following this we need to take actions. Will we take this action or will we take that action? Maybe we take this action and we end up in this point, and of course at this point there's of course an associated probability A given S, and after taking that action we might end up in some state here or another state here, right? And let's say we end up in this state, right? And this is associated with some, again, another probability. Right now I'm just writing this in those terms. So this is probability of S prime given you're in S and you take action A, blah blah blah. So we have all these probabilities that are dependent on which trajectory we took, right? So that's the thing. This is the situation we're in right now, because we're given a starting state st, right? And we take some action at, we end up in st plus 1. We take some action, I'm ignoring the rewards here, at plus 1, but there are also reward terms here, and so on until we reach some terminal state st, right? So if you're asked what is the probability of this trajectory happening, right? What's the probability of this trajectory happening? Well, we know how to actually represent this probability, right? this is actually equal to the probability that I take action AT the very first time, given that I'm in state ST, right, times the probability that I end up in some state ST plus 1, right? So this would be kind of like ST plus 2 given ST plus 1, comma A, right? This is what this would be. But I just wrote it roughly because you should be familiar with this by now. So this is we have this probability of taking action T given you in ST times the probability of ST plus 1, right? Given you're in ST and you take action AT, right? Now we're in ST plus 1, right? So what's the probability of taking action AT plus 1? Given we're in ST plus 1, and so on until we reach some probability as final time step, given that we're in some state final time step minus 1 and we take action at some final time step minus 1, right? This is the probability of the green trajectory. So this here, right, is showing the probability of probability of the trajectory. That's what this is showing essentially. So now that we have the probability of the trajectory, we can represent it as follows. This is equal to the product, right, from k is equal to t up to some point t minus 1 of pi ak, comma, sk times probability of sk plus 1 given that we're in sk and we take action ak. So this is just another way of writing what we have here, right, as this product term. So that's the probability of the trajectory under policy pi, right? So if we look at the probability of a trajectory under policy pi, and we look at the probability of the same trajectory, which is this trajectory we have here, right? This is our trajectory. That's what I mean by trajectory. So if we look at the probability of the trajectory under policy pi and the same trajectory under policy b, if we divide those two, right, probabilities, then we end up with what's known as the important sampling ratio, right? So what this is denoting is, okay, let me first write it down. The important sampling ratio, which is represented by this P. Let me try to write it better. So we have P from T until T minus 1, right? This is the important sampling ratio, which is the probability, the product from k is equals to t up to t minus 1 of pi ak, so this is given, I don't know why I put comma, given sk times p sk plus 1 over given sk comma ak divided, so we divide this by the probability of this trajectory. This is from k is equals to t up to again t minus 1 of policy b ak comma sk times the probability of sk plus 1 given sk comma ak, and we call this the importance sampling ratio, right? So basically what this is telling us is how likely is this trajectory under policy pi relative to, policy b. This is essentially what this is answering, right? So of course we can cancel these two terms out, and we are left with our pt until t minus 1 being equal to the product from k is equals to t up to t minus 1 of pi ak given sk divided by the product from k is equals to t up to t minus 1 of b ak given sk. Right, so this is essentially what we end up with. So this becomes our true importance sampling ratio. So as we see, it does not depend on the MDP because we cancel these two things out at the end of the day. So it seems to only be dependent on the trajectories and the policies themselves, right? This is essentially what this is. So we've established that we have our importance sampling ratio. So why do we need this, right? Because we wish to estimate the expected returns under the target policy, which is policy pi, but all we have are returns from the behavioral policy, right? And these returns actually have the wrong expectation, because if we look at the expectation of GT, right, given ST is equals to S, right? So this expectation, because we are generating, so if you remember from above, we have episodes that are following another policy B. So these are the episodes that we are using to generate the behavior. So the return is computed from those episodes. So the return is computed from episodes generated under the behavioral policy, which is B, which means this does not give us V pi of S, this gives us VB of S. But what was our goal? Our goal was V pi of S, right? This is what we want to know. But this only gave us VB of S. So how do we make sure that this expectation properly represents the expectation of GT under policy pi and not policy B? That's where the importance ratio comes to play, because the importance ratio transforms these returns to have the correct expectation value. So ultimately what we end up with is the expectation of the importance sampling ratio, which is PT, right, up to t minus 1, multiplied by GT, given ST is equals to S. Now this is equal to V pi of S, right? Because that was the whole goal of importance sampling. We're trying to find the expected value of one distribution by using the samples from another distribution, right? So this is what it is. But now we want to expand this further from how can we actually make this practical enough for us to be able to use it to actually estimate the value of a particular state, so that maybe I just want you to be able to, after this lecture, I want you to be able to implement your own off-policy algorithm just based on this information, right? Of course, in the future videos, we're going to go into the pseudocode and everything, but I just want to give you a more practical solution, at least at this point. So let's insert a new page. Okay. So now, for us to be able to do this, it is convenient to number time steps in a different way. So I'm gonna say this is our timeline, right? Let's say we have 0, 1, okay, 0, 1, 2, and then we reach some point 30, and we reach some point 50. So let's say this is our time steps, right? So let's say from 0 up to 50. This is episode number 1. So episode, let me just use a shorter notation. So this is episode 1. So let's assume that the next episode does not start again at time step 0, but rather at time step 51, because this will make it more convenient. So let's say it goes to 51, and then it goes up to 60, then it goes up to say 70, and then it terminates. So let's say this is our second episode. So let's say episode 2. And then episode 3 starts at time step 71, right? Let's say it goes up to episode 90, and then up to episode 110. It ends there, and this gives us episode number 3. And let's say episode number 4, the last one, starts at 111, goes up to 115, and ends at 120 or something like this, right? You'll understand why I'm using this representation, well, as per Sarton's book, of course, but there is a motivation for this. So this is where we are at this point, right? We number our time steps in this manner, right? And then let's actually look at our states, right? What do our states look like? So let's say our states, maybe use an orange color for the states. So let's say our states are represented by S prime, S double prime. So let's say these are all just different states up to some point, right? These are all just different states. I'm just generalizing here. So let's say at time step 2, we visited state S. So we're just saying we visited state S at time step 2. At time step 30, let's say we visited state S. Let's say at time step 60, we visited state S. Let's say, and then at time step 115, we visited state S. We didn't visit it in in episode 3, right? So these are the time steps that we visited as state S. And okay, let's say at time step, how can I say, 50, we visited state S prime, and let's say we also visited it at time step 90. This is S prime, where S prime and S are different states, so these are different. So S is not equal to S prime, right? These are all different states, right? So we are going to assume first visit Monte Carlo, right? First visit MC assumption. We're going to use first visit Monte Carlo. We're not going to do every visit, but you'll see that the analysis we're making here can be very easily extended to every visit. So we're doing first visit Monte Carlo here. So what are we trying to do here? Well, let's use this notation now. So we're going to use the notation T S, right, to be the number of episodes that the episode that actually contain the state that we visited, or more specifically the time steps, right, that contain the state that we visited under the first visit assumption. So T of S, right, where we're saying S is here. So S was visited. This is just a set of every time we visited S for the first time within an episode, right? So here we visited S at time step 2, so we put 2 here. We visited S. We visited S at time step 30. So if this was every visit, we would put 30 here, but since this is first visit, we're going to be ignoring this 30 because we only care about the first visit. Okay, episode 2, we visited S at time step 60, and that's the first time we visited it, and that's it. And then episode 3, we didn't visit S, so we ignore it. And episode 4, we visited S at time step 115, right? So that's what T of S is here. And we can also have T of S prime here be equal to, we visited it at time step say 50, we visited it at time step 90, right? So that's what TS is. So when we look at the cardinality of TS, right, this is now essentially representing number of episodes containing state S. This is essentially what this is representing in the first visit assumption. So if it was every visit, well, we would count every single time that we visit S across all the episodes. That's what this would represent. But since it's only first visit, it's only showing like number of episodes containing the state S. In this case, imagine the what do you call it? The cardinality of TS here is so tau S. I'm not sure the Greek letter for this is, but anyway, this is actually equal to 4. So to 3, and here the cardinality is 2, right? So here it's 3, and here it's 2. That's what the cardinality is. Okay. So we're using this representation. And then, so here we're using this funny tau thing, but let's use another different notation. So we're going to have a lot of this notation. So we have T, normal capital T, T, right? So what is this going to denote? This is going to denote the first time of termination following time t, right? So the first time we terminate following time t. So for instance, if we're asked what's t of 30, well, if we look here, the first time we actually terminate starting from time step 30 is at time step 50, right? So t of 30 is equal to 50, okay, and t of 0 is also equal to 50, for example, because again the first time we terminate starting here is at time step 50. But if we're asked something like what's t of 90, so following time step 90, what's the first time we terminate? It's 110, so this is equal to 110, right? So this is what this capital T is representing, which is different from this tau thing. So this is what we have, right? And then let's modify our definition of the return a bit. So we will define GT, which is our return, to be the return from T, time step T, until TT. So if we're computing the return from this state time step 30, from this let's say we're computing the return from this state, since we're doing first visit, time step 2, we sum all the rewards from time step 2 until time step 50, right? Because T here is 2 and TT is 50. So in that case, we would have, if T is equals to 2, that means T is equals to 50. So we'll be computing the returns from this time step until this time step. So that's what the return is. So it's computed from some time step until the first time of termination following that time step. So this is how we define the return. Okay. So now that we have this as our definition for the return, we want to now look at the set of returns for a particular state, which we represent by this notation. So if GT for T is an element of this tau s, right? Maybe I should use the same color I used here. So it's an element of tau s, right? So what is this representing essentially? Well, this is a set. Oh, I used a much different color. Maybe that's not bad. So a set of returns pertaining to state S. Why are these returns pertaining to state S? Because what did we say T of S is? This is representing, under the first visit assumption, right, is representing the time steps in which we visit state S, right? So since those are the time steps we visit state S, if we look at the returns from those time steps, we will get the returns pertaining to state S, right? This is the idea. So equally, when we have something like this pt until t minus 1, right? T is an element of tau s, or whatever this Greek letter is. So these are the important sampling ratios, right? So these are our important sampling ratios for those time steps that we visit state S. These are our important sampling ratios. So now that we know what this is, the next thing we want to do is estimate V pi of S, right? By using Monte Carlo. Well, this is equal to, so now I'm just gonna try to use the same color everywhere. The summation, T is an element of TS, so we look at every single time step where we visit state S of PT, right? The important sampling ratio, minus 1. This is the important sampling ratio, right? Multiplied, so just so that we can see these things are different, maybe I should use a different color here. So multiplied by GT, right? Divided by the cardinality of T of S. So we look at the returns, right, starting from a particular state. We multiply it by the important sampling ratio. We sum up those things and we divide them by the cardinality of TS, right? And this is called ordinary importance sampling. So this is known as ordinary importance sampling. Okay, that's fine and all, but now when we have another alternative for this, where we compute V pi of S, right, as to be equal to the summation over T is an element of TS. So just to speed things up, I'm just going to write this down quickly so that you know. So you should be able to follow by now. So this is divided by, but now instead of dividing by the cardinality of TS, we just divide by the sum, right? Because this is, we're weighing based on the important samples. So important sampling ratios, sorry. This is what we're weighing using, right? And it's 0 if denominator is 0, right? So what do we actually call this? This is known as weighted importance sampling. So there are a couple of differences and like between these two methods of importance sampling, and that's something that I will touch on in the next lecture, at least in this module. So until this point, I'm going to stop at this point and hope that this was at least clear and informative to you, and I hope it's something that you can actually make use of when designing your own algorithms in the future. So I'll end this lecture here. Thank you kindly.